classical mechanics. And I have to come back to the pendulum because it's kind of full circle. And I told my students I would do this. So I'm going to show you very briefly what we do with the Hamiltonian. We've talked about Lagrangian, and then I'm going to go over the Hamiltonian. Normally, I would do more Hamiltonian stuff in the second semester of physics. And a lot of people get confused in classical mechanics with the Hamiltonian because it's like, I don't know what you're doing, the same thing as the Lagrangian. But let's just look at the pendulum. And I want to solve the equation of motion for a pendulum using Newtonian mechanics, and then Lagrangian mechanics, and then Hamiltonian mechanics, and then I'll talk about each one during that time. And so it's going to be fun. We're going to just have a fun time. Okay, pendulum, mass on a string of length r, displaced by an angle theta. Let's use Newtonian mechanics. So Newtonian mechanics says that the total, this is net. The net force is mass times acceleration. And if I know those forces, I can find the acceleration and everything's going to be great. And that's what Newtonian mechanics does. Now, in this particular case, it's not easy, right? Because I have the downward gravitational force mg, and then I have this tension force T like that, which I probably shouldn't use T, but there we are. And I don't know what T is. T is the force of constraint. T is whatever value it needs to be in order to keep this moving in a circle of radius r. So that's my problem right there. T is my problem. I don't know it. Now, I can put Hamiltonian right there. I'll put it down there. So I can solve this problem by using polar coordinates. That's one way. There's a bunch of tricks to solve a pendulum. But the one that we used before is to use polar coordinates. And I derived this before. It's somewhere in my playlist. You can find it. If you can't, let me know. But the acceleration in polar coordinates, if I use r and theta to represent this position, then I get this for the acceleration in the r direction and this for the acceleration in the theta direction. Now, I can write down my forces in polar coordinates and I have something really nice. But let's just do it. Okay, so let's write down the forces in polar coordinates. I have, this is some angle theta, so Fr, the r component, is going to be, what forces act in the r direction is going to be negative, r is that way, so it's going to be negative t plus mg cosine theta, right, because that's the component of the gravitational force in that direction, and that's going to be equal to this mass times r double dot minus r theta dot squared. Now, but what happens here is that r is constant. I know that has to be true. So r dot is 0, r double dot is 0. But in the end, I don't get anything useful, right? I can't solve for anything there. So it's not helping. Let's look at the theta direction. In the theta direction, I have what forces act in the theta direction. So that's positive theta. So I'm looking at this component of the gravitational force. So it's negative mg sine theta. Negative mg sine theta. So that's my force in the direction. Now that's going to be equal to the mass times acceleration in the theta direction, which is this. So I'm going to go ahead and put in little r is capital R. So it's capital R theta dot, and then that term has an r dot that goes away, 0. So that's it. Okay, so wait, that's the double dot. I was looking at that like, wait, something's not right. So I can just solve this for theta double dot. Let's do that. Mass cancels, and I get theta double dot is negative g over r sine theta. And that is my equation of motion for a pendulum. We've seen that before many times. Of course, if theta is very small, then sine theta is approximately equal to theta. So I get theta double dot is negative g over r theta. And then you get simple harmonic motion. So that's but that's the real version. And solving that, that's fine. We can do that a whole bunch of times. But we're just trying to get here. That's what our mechanics says. Get there, get a differential equation. So Newtonian mechanics, not too bad. You got to use polar coordinates. If you don't want to use polar coordinates, whew, I don't know what to tell you, because that's fun. Okay, Newtonian. It's fine. It's not first freshman level physics, even though that's in there a lot. Now let's use Lagrangian. So in Lagrangian mechanics, what we do is that we define a generalized coordinate to describe the system. It doesn't have to be Cartesian. And then we create the Lagrangian, which is the kinetic energy minus the potential. And then we use Euler-Lagrange equation to find equations of motion. And this just says that what we call the action is an integral, and that path of the action is minimized for the real solution. But don't worry about that. So we can just use it. Now, we do have a problem here. What's our generalized coordinate? It seems obvious that we're going to use theta. I mean, that completely describes the system. But then, how do I get the kinetic energy in polar coordinates? Now, you could just say, it's just easy, right? And I get it, it's easy. But we're going to do it the full way, because I respect you. So what we do is, I say T is 1/2 m x dot squared plus y dot squared. Because I know the kinetic energy in Cartesian coordinates. So I'm going to write it in Cartesian coordinates. And then, if I know x in Cartesian coordinates compared to this, which is going to be r times sine of theta, right? That's right. That's the distance. And then y is negative r cosine theta. I can take my derivatives of my Cartesian coordinates and plug them in there. So x dot is going to be equal to r theta dot cosine theta. Y dot is r theta dot sine theta. Negative, right. So remember, if I take the derivative of r as a constant, if I take the derivative of this, I get cosine theta, but I have to take the derivative of theta too, and that's where that theta dot comes from. And then if I take x dot squared plus y dot squared, I get r squared theta dot squared cosine squared theta plus sine squared theta. And this happens a lot, and that's 1. So it's not so bad. Now I can write my potential. It's going to be equal to mgy, but y is negative mg cosine theta. Negative mg, or. Now my Lagrangian is going to be 1/2 m times x dot squared plus y dot squared, which is r squared theta dot squared, minus this, so plus mg r cosine theta. Now I can apply my Euler-Lagrange equation right there. So, and I'm going to need this. So let me put this up here. I'm going to need it for the next step too. Oh, right there. I'll put it over here. I don't want to lose it, even though it's not hard to get. L 1/2 m r squared theta dot squared plus mg r cosine theta. Okay, that's fine. So now I can say the partial of L with respect to theta, because I'm doing this over here, right? I'm going to do these two terms. So the partial of L with respect to theta, it's just a partial derivative. Where is there a theta? Only right there. So the partial derivative of cosine theta is negative sine theta. So I get negative mg r sine theta. Now let's do the partial of L with respect to theta dot, which is the only place it comes up is right here. So I get m r squared theta dot. Now I need to take the time derivative of that. And the only thing that changes with time is theta dot. So I get theta double dot. Now these two terms have to be equal to each other because they're added together to be 0. Can't see that. So I get m r squared theta double dot equals negative mg r sine theta. Mass cancels. Theta double dot is negative g over r sine theta. The same thing, right? Of course we get the same thing. It's still a pendulum. It's not going to move differently because we said, oh, let's use Lagrangian mechanics. It's still the same pendulum, so we get the same thing. I think that's a pretty good solution. Okay. Finally, the Hamiltonian. Okay. So the Hamiltonian says right here that we can define a generalized momentum as the partial of the Lagrangian with respect to our coordinate theta dot. If you have more than one coordinate, that's fine. You can do more than one momentums. And then my Hamiltonian is going to be p theta dot minus L. And then I have the big difference between the Lagrangian and the Hamiltonian is the Lagrangian gives you a second order differential equation, theta double dot. Here we get two first order differential equations. Theta dot is the partial of h with respect to p. P dot is negative the partial of h with respect to theta. So let's find p. That's number one, p. So p is the partial of L with respect to theta dot. And see, I put it up there. I got one theta dot, so it's going to be m r squared theta dot. Now I need to find the Hamiltonian. That's going to be p theta dot minus L. So let's just put in p times, I'm going to write it like this. No. Let's just write it as p theta dot minus 1/2 m r squared theta dot squared minus m g r cosine theta. Okay, so if we look over here to our Hamiltonian, we want to get it in terms of theta and p. So I don't want any p theta dots. So that's my problem. So up here, I can see that this theta dot. So if I put in, if you just solve this for theta dot, how about that? Theta dot is going to be p over m r squared. So down here I get p times p, so p squared over m r squared. And then this is going to be equal to minus 1/2 p squared over m r squared. Is that right? So m r squared, no, that's theta dot, so that's good. I get p squared, over 2 m r squared. Yeah, I think that's right. P squared over 2 m r. Yeah, that's right. And then minus m g r cosine theta. And then these two terms combine together, and I get h is p squared over 2 m r squared minus m g r cosine theta. Is that what I got before? Because I make this mistake all the time. Yep, that's right. Okay, notice that that is the kinetic energy and that is the potential. And so in this case, the Hamiltonian is kinetic plus potential. So it's the total energy. It's not always, it is here. Okay, so now I have the Hamiltonian. I can apply my Hamiltonian equations. So let's get rid of this stuff, which I probably shouldn't do. And I'm going to say theta dot is the partial of h with respect to p. So if I take the partial of this with respect to p, I get p over m r squared, which is what I had before. Okay, and then if I take, if I find p, it's going to be negative the partial of h with respect to theta. So that's going to be negative m g r sine theta. Because I have a negative, I get another negative, I have another negative, so it's still negative. Okay. Now, let's just solve this. Now we want to get, that's really the answer. We have two first order differential equations for theta and p. But let's just take this and, what did I do? I'm not good with this. See, so p dot, okay, so p dot, that's right. So I have down here, oh, this is p dot. Oh, that's why, that's p dot. So let's solve this for p. P is going to be m r squared theta dot. So p dot, I can take the derivative, it's just going to be m r squared theta double dot. And if I put that in right here, I get m r squared theta double dot negative m g r sine theta. And then you solve for theta double dot, you get it. Negative g over r sine theta. So again, back to that same equation. So just a couple of other comments about Hamiltonian because it seems roundabout here. But the thing is, number one, the Hamiltonian is used in quantum mechanics, right? H psi equals E psi. That's the Hamiltonian, but we use operators for the momentum and the position. So that's why it becomes the Schrodinger's equation. Number two, it turns out that this is very useful in statistical mechanics too. they use the Hamiltonian. But in classical mechanics, it doesn't really help us that much. Lagrangian's better. Okay, so there's your quick intro to Hamiltonian. That's what I was doing that for. Play this down below. I already said that.